I want to talk about the work that we're doing at the Space Sciences Lab at Berkeley on microfluidic detection. This is the first time I've been at this meeting, but you should realize that I've been working in the microfluidics area for about 20 years, mostly on genomics and high sensitivity analytical detection. And then I connected up with Jeff Bada with the Mars mission and the URI instrument, and got into this direction, which is a lot of fun. My collaborators are Anna Butterworth and at the Space Sciences Lab at Berkeley, James New and Laura Casto, postdocs, and Matin Golzar. We're working with Jungkyu Kim at Texas Tech on the microfluidics and the microprocessing fluid motion. The impact work that feeds into the EOA is being done at the impact group at Kent, and we're also collaborating with Amanda Stockton at Georgia Tech. Now the basic idea, is there a pointer? Yes, no?
Yeah, it's just
on this thing. This looks dangerous.
Yeah, it's one of those buttons.
Oh, got it, okay. The basic idea is a core microfluidic analyzer. You've heard about CE before. This is integrated into these components that basically enable us to do high sensitivity organic analysis. Then there are a variety of inputs. In the case of Enceladus, you have particles coming into a plume capture system. For the MOAB application, which could be landed on Enceladus or Europa, you have a sample funnel. You've heard this all before. With our 100 picomolar sensitivity, we meet the detection requirements that came out of the science definition team. But for Enceladus, it gets a little trickier because instead of getting 1 gram of material, you're only getting a few tens to hundreds of micrograms. So we've been doing a lot of work figuring out the capture process and organic survival, and so far, basically in terms of defining mission feasibility, it looks like we get significant organic capture and survival up to about 3 kilometer per second impacts, and slower is a bit better. That means in one pass, you get an interesting result of 40 part per billion detectivity, but probably not enough for life detection. But with 10 passes, you get into a regime where that would be actually quite interesting. Now, the basic concept of this, I'll go through quickly, is looking for biofocusing and amplification of molecular complexity caused by life. That amplification can be fatty acid chain length variation, chirality, amino acid focusing, and so on. But the big point about this is that molecular analysis is highly leveraged because, for example, on Earth, a bacterial cell gives you 1 billion readout mechanisms, such as amino acids. So there's a 10 to the 9 gain when you look at the molecular components of a cell. So the idea is to label those biosignature molecules and to do functional group-specific fluorescent dyes. So we segregate the molecular population and then go on to electrophoretic analysis. Now, a little heritage. This was first developed at the prototype stage in our group by Jim Scheer some 15 years ago. Confocal detection, a stack of wafers, 2 pieces of glass here that define the capillary electrophoresis channel, and microfluidics I'll tell you about for manipulating things on the chip at very low volume. Confocal laser fluorescence gets you 100 picomolar sensitivity, and the basic point is if you can't, if you don't see it, it doesn't matter. So high sensitivity is really critical in this game. Now, a key part of this is the manipulation of the fluids. And back in 2003, Will Grover and my group invented these pneumatic valves where you apply pneumatic pressure to essentially open a deformable membrane to open a valve or close it. These are normally closed valves. You can gang 3 together to make a pump, as was described early in the conference. And we invented it, we patented it. It's actually part of a commercial product sold by Thermo Fisher right now. It was actually quite successful and enables doing quite a few interesting things. Now, illustrating this functional group-specific labeling, if you take carboxylic acids and hit them with Cascade Blue, you can light those up selectively. Here's an example from Mojave Bat Cave. This is in my era in my life when I was doing field trials. So it's a very high sensitivity apparatus. Everybody else should try to analyze bat shit. I bet you can't do it, okay? We can also label aldehydes and ketones. This is my most famous paper where we actually analyzed various wines from the California industry. Got the highest citation of any paper I ever did. You can also, of course, label amines and amino acids. This is a separation of about 50 different components, which is just a standard. But basically, like everybody else, we went to the Atacama Desert. We ran supercritical water extraction. We did analysis. We saw part per billion detectivity, saw chirality in the Atacama Desert. And notice that was published in 2007, so we did this like over 10 years ago. Okay, so that's the end of my prototype instrument field trials life. And I said, I'm done with this. I'm going to focus on making flight instruments that are basically specifically designed in their physical layout, in the materials you put in and everything else, so we transform directly to flight with these technologies. So that's how it fits together. There's this core organic analyzer. The MOAB thing, which is IC2 funding, has just started. There's a component which is accommodation. Now that we have specific science goals that came out with the SDT, we have specific target concentrations and separations we want to do. We're getting going on that. And the sample input, this sample input is a funnel. It is purely sort of notional because we just had the meeting with the Cadmes guys to figure out what the nature of that sample transport is going to be. But it will obviously be introduction of solid filtration and generating fluids. So what is the state of the core analyzer? That's outlined here, and I'll go through it. The basic point here is, first, there's a macrofluidic system that's been designed by the engineers at JPL, and I should point out here that my focus here is on making very simple, very robust technology, high TRL, that is designed by people who have built flight instruments before. We want it simple, we want it integrated, we want it totally autonomous, we want to do one thing really well and have low risk. So the macrofluidics is shown here, where we have the gas reservoirs, pneumatics, and water storage chambers. That's in green in this CAD design. And you can see the hard components that we fabricated here. The chip that I'll go into in more detail is contained in this orange structure, and here's a picture of the chip in the prototype fabricated chamber. There's also a confocal detection system, shown in purple, that fits in here. And now I'm going to go through all these various components. Now, an important part about this is sort of the transfer function. This is what we call sort of level 1 requirements. How do you get from 1 gram of material with 0.1 ppb organics all the way through to 100 picomolar detection at our detection system? And this shows that transfer function. I think in the interest of time, I'm not going to read all these numbers, just show you that it exists and we've worked it out. An important part about this for others is that after we get roughly 1 milliliter of dissolved and filtered material, we really only need 100 microliters of this. So most likely there's about 900 microliters that can go to other instruments. And these results allow us to meet all the science goals that are defined by the science definition team for Europa. Now, so here is an image of the chips we're now making. This wafer, you can see the separation channel. It is the cross and the separation. You've heard a lot of talks about this, so I won't go through the details. These are fabricated in the Nano Lab at Berkeley on 100 millimeter wafers. It's 2 pieces of glass. One surface is etched. They are then thermally fused together. This channel format, 15 centimeters long. They're 100 by 30 micron cross-section channels. We're using 2 channels because, if you get to Europa and one of them clogs, you're kind of screwed. So we're doing 2 redundant separation channels and detection systems. And you get these very fast separations that have already been talked about. The main point is that, you can make these things. You can carry them around in your suitcase. Kevin can look at it. This is very robust, solid technology. And what you have to remember is what I just showed you has the CE system. It has all the valves. It has all the fluidic processing. There are no external swage lock connectors or tubing. It's just a chunk of stuff that you can pass around, okay? It's very robust. So the fluidic system that I just handed to Kevin is what we call a programmable microfluidic analyzer. This is made by Jungkyu Kim at Texas Tech. And if you go around this, the circumferential inputs are the pneumatic inputs. Those are indicated in blue. So here there are 4 inputs that control these valves that control the filling of the CE system. These ganged inputs control the central processor. This is essentially a programmable automaton that allows you to route fluids to any point. That was invented by Will Grover in my group. And this is an array of sample storage reservoirs. The sample is pumped to the reservoirs by that macrofluidic system. And then we use these 3 valve pumps to move fluids around and mix the sample with the reagents and get a reaction. And I showed you the CAD. Here's a picture of the device, and here's the device. So we've gone all the way, okay? So these systems are very nice. We're currently integrating that chip into this manifold. This is a circular manifold that has the solenoids. The connection between the solenoids are controlling pressure and vacuum that go into the chip and control the valves. So it's a nice compact structure that's really no bigger than the 100 millimeter diameter wafer. You can see the high voltage inputs that come in. The chip is covered, so we have an ambient pressure over it, over any fluids that are exposed, so we don't have to deal with evaporation and electrochemical breakdown. The valve manifold and all of that has been assembled here. We're using pigtails to connect the circuit board up to the manifold, but it can be also directly soldered in place. And all of this makes up what we call a technology demonstration unit, which has actually just been assembled in our lab and is now undergoing functional testing. And I point out, this is all designed by the engineers at Space Sciences Lab. This is the format that will fly. Every component we're putting in here, every design is designed to be flyable material, a component that has flight heritage, or a component that has a pathway to flight. So the overall structure of this is shown here. This is the EOA TDU assembly. Of course, we just got MOAB money, so we haven't built anything with it yet. So this is really an outline of the EOA. Here's the CAD of the system. The power supplies are conventional because we didn't get money to build those. The chips going in there. Here's the manifold, the macrofluidics. There's the confocal detection system. And for EOA, of course, there's a particle capture system, but the patent's pending on that structure, so I can't show it to you. We'll probably talk more about how you achieve those detection sensitivities for Enceladus impacts, probably at AGU in December. So last slide, the Berkeley Space Sciences Lab is really pioneering the fabrication of these microfluidic instruments, characterizing organic biomarkers. I think functional group specific labeling really enables you to segregate the molecular population and is very agnostic. It's not just amino acids. Basically, any molecule that shows up with aldehyde, ketone, amine, or carboxylic acid, whatever life gives us or life doesn't give us, we can label it and we can segregate it and we can detect it with high sensitivity. And we expect to be at TRL 6 with a clear pathway to 7 by basically somewhere between 2021 and 2022, which unfortunately now looks like it might be early, but we'll see what happens. Okay, so thank you very much. Happy to answer any questions.
Questions?
Frank Bosberg, FU Berlin. So can the system handle salt-saturated brines? Does that matter?
Can it handle what?
Can the system salt-saturated brines?
Yes, we were the first to show that you could handle saturated brine. We actually got samples from the Saline Valley in Death Valley, and the way you do that is there's 2 solutions. One that Zach mentioned already was dilution, but the key part about that is there's 2 key points. One is you make sure you pick a buffer which has sufficient buffer capacity to deal with any high or low pH. We did Rio Tinto samples too. I can send you a reference for a paper on this. But you know, the killer is if you dilute, you lose sensitivity. And that's why we developed these Pacific Blue reagents, which actually got us about a factor of 100 times better sensitivity than the earlier work we did when we were working with Jeff. So the basic point is if you have super high sensitivity, you can trade that sensitivity to solve problems. And you've described one of the problems that we solve with that, exploiting that sensitivity.
Excellent. Any other questions? Okay, let's move on.